Today we will see in detail about gradient, divergence and curl, which is a very important concept for electromagnetic to understand the electromagnetic theory. Uh, I am going to give full course on electromagnetic theory, which is intended to both science and engineering students. Before going into further detail, we will see about del operator. Del operator is represented by this simple nebula, which is equal to partial derivative of t partial derivative of x multiplied by I partial derivative of y with, multiplied by j partial derivative with respect to z multiplied by k. Here I, j, k are unit vector along x, y, z directions respectively. So when some function act on this del operator, you can write like this. That is delta f over delta xi plus delta f over delta yj plus delta f over delta jk. Remember that del is not a vector in the usual sense. It's not a vector. Uh, and in fact, it does not mean much until we provide with the function act upon. So it depends upon on which function it act upon. Further, it does not multiply f, rather it is an instruction to differentiate what values. To be precise, we say del is a vector operator that act upon, it's not a vector but vector operator that acts upon f, not a vector that multiplies f. This is not a vector that multiplies f. This is some operator. If you take del squared is called Laplacian operator. So del operator is in Cartesian coordinate. We have defined like this. After understanding this, we will see what is gradient, divergence, and curl. Here, we will take one small example to understand what is a gradient. See, I have taken one blue color rectangular pass. Take it as a very good conductor metal. I am heating from the downwards. So after some time, the rod will be, because it's a metal, uh, it get heated up uniformly throughout x-axis. That is horizontally, it is heated. Uniform heat you can observe after a certain period of time. Now you measure the temperature parallel to this rod, so you may not find much variation. Uh, However, if you measure the temperature along this y-axis, there is lot of variation. You can easily understand. So the temperature is direction dependent. If you take like this temperature, like this direction or this way, or this positive x-axis this way, the temperature depends on the direction. So if you make a del operator, you can take it in three dimensions. Assume that you have a one room and the floor is uniformly heated with metal. uh, then the radiation will be radiation must not vary along horizontal axis, but however in the vertical axis it variation will be too high. So naturally, though temperature is scalar quantity, the temperature difference along different direction will differ, which is the characteristic of a vector. See, here I have taken del operator act upon the temperature T. So I will get del operator by definition this one, and we will get this result. Along x direction, y direction, and z direction, the temperature variation will be different. Uh, so, del t is a vector quantity with the three components. In the Cartesian coordinate, it has three components x, y, z. It is the generalized derivative we have been looking for. So, what is the geometrical interpretation of gradient? Like any vector, the gradient has a magnitude and direction. That means it will behave like a vector. Though the temperature is scalar quantity, it behaves like a vector quantity. We will see about the divergence. It is defined as the amount of flux diverging from a unit volume element per second around that point. Uh, that is, for example, you take a positive charge, then field will be along this direction outward. So it will diverge from that point. If it is negative charge, this is also divergence, but field line comes inside the negative charge. So this is the positive divergence. A positive divergence is indicating flow away from the point under consideration, that is source. The field line are converging into small volume surrounding to that point is divergence of vector is negative. In this case, divergence is negative. It acts as a sink. Source means the field line goes away, or the some potential or field, whatever may, or flow of charge, current, water, whatever may be, it flows outwards, then it diverges. It is called source. If it is coming inside, then it is called sink. It is positive divergence. This one is the negative divergence. If the field line entering to that particular point is equal to field line leaving around that point, uh, then the divergence of a vector is zero. That means there is no source or sink. So this is another important point. So now we will see the divergence of a vector quantity. Let F be the vector. It has a F1 component, F1 along x direction, F2 along y direction, and F3 along z direction. This is the function F. If you take dot product over the del operator, this is the del operator. So if you take dot product, only I into I will become 1, all other component will become 0. You know the meaning of dot product. So finally you will end up with delta F1 over delta X plus delta F2 over delta Y plus delta F3 over delta Z. So this is the dot product. Naturally, I need not say it's a scalar. So dot product is a scalar quantity. Remember that F is a vector. So in the case of gradient operation, when you take a gradient like water flow, mass, or the charge flow, or whatever may be, or temperature, we have taken temperature as our example. Temperature is a scalar. When you take a gradient of it, it behave like a vector that we have seen. Here, the vector F will represent the divergence of F represents a scalar quantity. The vector become scalar. That is, we have a real-time example. First two Maxwell equation is a divergence equation. So from that equation, we know divergence E, where E is the electric field, which is a vector quantity, is equal to rho pi epsilon naught. Here epsilon naught is a scalar and charge density also scalar. This is the best example for divergence operation. Similarly here, divergence P equal to 0. Meaning of this is, you know very well, there is no monopole. So magnetic field, if you split the magnet into two pieces, then again you will have south and north pole. You cannot separate south pole or north pole. So there may not be any divergence. That is the meaning of this. 0 is a scalar quantity. So from Maxwell equation itself, we have seen two examples about the divergence. That is divergence of vector will become a scalar. Here, magnetic field is a vector field, so 0 is a scalar. Then we will go about the curl. Now we will see what is curl. Curl is a measure of how much the vector curls around the point under consideration. I can give you some simple example. If you throw a stone in the pond, water will curl. You might have seen it. The curl of the field is formally defined as circulation density at each point of the field, how much it circulate. So we are going to see so many example for this curl in our course. A vector field whose curl is 0 is called irrotational. So if curl 0 means is nothing happening, so it is not rotating. So it is called irrotational. We are going to see example for this. The curl is form of differentiation for vector field. So it is one form of differentiation in the vector field that we are going to see now. Curl of a vector is defined like this. It can be written in matrix form ijk, where ijk are unit vector, and this is partial derivative with respect to x, y, z. This f is the f1, f2, f3 are the components of f along x, y, z direction. Just now we have seen it's another form of differential equation. See, you have a differentiation, partial differential equation. This, if you expand this, you will get to naturally the partial differential equation. So, in terms, curl tends to be curl of a vector tends to be into another vector. The best example we can see is from the Maxwell equation itself. Maxwell, this is Maxwell third and fourth equation. Here, curl E. E is the vector quantity which will become time derivative of magnetic field. This is also vector quantity. That is, curl operation turns one vector into another vector form. Similarly, curl P is equal to mu naught epsilon naught partial time derivative of E plus mu naught J. Here E and J are the vector quantity. So P can be P turns into E and J. So the curl convert one form of vector into the another form of vector ultimately. So this is about the curl operation. This is very fundamental for electromagnetic theory. We are going to use this frequently in our course. Thank you very much for watching my videos and supporting me continuously. If you have any question, kindly send it to the following mail ID vasimku@gmail.com. Kindly subscribe my channel. My YouTube channel ID is youtube.com/at vasubphysics. Thank you very much.